This talk is part of a series presented by the TechAide AI4Good conference and hackathon. Our goal with this virtual event is to highlight technological innovation driven by AI and directed towards beneficial areas such as health, the environment, accessibility, and human rights. Importantly, we also aim at raising money for TechAide, a nonprofit dedicated to fighting poverty and social exclusion. And this is where you can help. Please consider donating by clicking the corresponding link in the description section of this video. Any amount will be greatly appreciated. Also, if you are watching this before November 12, 2020, consider registering to our event for a chance to ask questions and interact with our great speakers. This event would not have been possible without the help of our sponsors such as DeepMind, Ubisoft, Ivado, and Dell Technologies. We thank them for their generous support, and please visit our website for our full list of sponsors and partners. Finally, I'd like to give a special shout out to one of our sponsors. For those who don't know yet, Ubisoft La Forge is a collaborative space created by my colleague Yves Jacquier. At Ubisoft Montreal, they bring together experts from their studio and experts from the academic sector to accelerate R&D through prototyping. Through this process, they want to complement academic learnings while testing the potential benefits and technological innovations in virtual worlds, fill the gap between theory and practice. I invite you to visit their website, laforge.ubisoft.com, where you will find articles from their researchers and videos showing their prototypes. And with that, I'll leave you to enjoy our featured presentation.
Hi, everyone. I'm going to talk to you today a little bit about my research and my opinion on explainability in the context of machine learning and health. But first, I'd like to encourage you to donate to TechAide and support their work on fighting poverty and social exclusion. So the title of my talk today is Don't Explain Yourself. And we're going to talk about exploring healthy models in machine learning for health. I'm Dr. Marzyeh Ghassemi. I got my PhD at MIT a couple of years ago, and I am now an assistant professor at the University of Toronto in both computer science and medicine. I'm also a Canadian CFAR AI chair at the Vector Institute. And the reason that I think we should focus on healthy models, and I'll define what I mean by that, robust, private, and fair models in machine learning for health, are that machine learning and algorithms more generally have been a part of health for a while. So especially in acute care environments like the intensive care unit, we've seen algorithms that are used, thresholds, alarms for quite some time. But the reason that the conversation has changed recently, and there's been more focus on machine learning tools, is that suddenly we have algorithms and models that are achieving at or above human performance across a range of tasks in the human lifespan. And so suddenly the conversation has shifted from, can this calculator help me with a particular task, to could the calculator do the task and remove some of the tediousness, or in a particularly high impact setting like with COVID, could it help to triage some patients? However, there are a lot of barriers to having real deployable machine learning models in a health setting. My lab focuses on creating actionable insights in human health. We have research into what models are healthy. So this is trying to make models work well in a healthcare setting on sparse, heterogeneous, and noisy healthcare data. We also try to work in what healthcare is healthy. And by that, I mean trying to identify, even if you have the best model with high performance, is it now robust, private, and fair? So something we would feel comfortable deploying because human lives are at stake. And then finally, what behaviors are healthy? So are there individuals in the intensive care units or in primary care? Generally, are there clinical staff that could benefit from this model? Because even if it's an accurate, fair, robust, private model, if the humans who actually deliver the care can't or won't use it, it's not going to be beneficial. So when I work in machine learning for health, I usually partner with a clinical team or a specific doctor. And usually what happens is one of the things that we have a conversation about very early on is the idea of transparency. And so you might say, why would you talk about transparency so early on? I think, my personal opinion, is that this is due to interdisciplinary mismatch in expertise and expectations. So often a machine learning person will come in and say, oh, you seem to have a hard problem that your field has been struggling with for years. Struggle no more. My algorithms can save you. And then 6 months later or a PhD later, you'll discover, oh, wow, this was really hard. I don't think that we actually did this in a way that's meaningful for you. And one thing I think that is used by clinical staff and other experts to sort of guard against this is this demand that, well, we need models that are explainable, that are transparent. And I think that's in large part in order to ensure that they don't get a product from a machine learning expert that they can't use. And I think this is the wrong bandage for this solution. And I'll argue that in this presentation. So there are many forms of transparency. I'm going to focus in the talk today on explainability, which is a very popular definition for transparency in models. So you can get people to trust explanations. So your first question might be, okay, do explanations even work? And the answer is yes. So there's very good work in the robotics literature by people like Ayanna Howard, demonstrating that humans overtrust robotic systems, actually, in scenarios where they either believe that the robot can perform a function that they can't, or the expectation is that the system will mitigate risks. And in health, we actually have both of those things, right? So robotic systems or machines like MRI machines perform a function that you cannot. And when you hear alarms in the intensive care unit, there's an expectation that the system will be mitigating risks. Or if you have order sets that are recommended for medications, there's an expectation that you wouldn't prescribe two medications that are counterindicated with one another. But how does this work with medical data? Does this have anything to do with medical data? The reason I thought it might initially is because there's some interesting work by Sanmi Kuyeja's group that demonstrated that if you generate fake images, so these are generative adversarial network scans that are trying to generate chest x-rays, right? This was the first part of their research study. It wasn't meant to be a main outcome. So the first part was, can we just generate x-ray images that fool clinicians, right? So they know better than chance. Can they tell whether an image was generated by a real patient's chest x-ray or whether it's synthetically GAN generated? And if this was true, if they were just generating good enough images that people couldn't tell them apart, you would see most people would lie along this rate 50% line. Or if the GAN images were just not that good, then you would see that most people would lie below this 50% line because they would favor the real images. They would proportionally tend to choose real images as the real images. But that's not what they found. They actually found that individual doctors have very strong preferences on whether they believe that the GAN images are real, as one person is showing here, or whether they believe the real images are real, as shown here. So that's a little bit concerning because health is actually about human decision-making. And so we did a brief study recently where we said, okay, ultimately the goal here is improved care. So we want to measure how advice impacts both expert and non-expert clinical decision-making. We also want to look at within decision-making, what role does the accuracy of the advice play? And if the advice is rated differently, if you just think it's from an AI. So the experiment that we set up was giving clinicians two types, experts who are radiologists, they see x-rays all the time, and non-experts, internal and emergency medicine, IM, doctors who see x-rays, but it's not their main task, an x-ray image. And then we varied two things. We varied whether we said the source of the advice was human or AI. In the end, it was just us, right? There was no AI here. And whether the advice was accurate or inaccurate. So those are the two things we varied, the purported source of the advice and the accuracy of the advice. And then we asked them two things. What is the quality of the advice? And then we measured what they indicated for the final diagnosis, right? And so, for example, if the correct diagnosis is pneumonia, but we incorrectly recommend something like a right sternoclavicular dislocation, they would change that and say, no, we need something else. So what we found unexpectedly is that there's a big difference in clinical attitudes towards advice from different sources. So radiologists, shown here, rate the AI advice as significantly lower quality than the human advice, even though it's the same advice. We also found that this effect is not true in the IM/EM doctors, but neither kind of doctor has a significant difference in their accuracy by advice type. And that makes sense. It's the same advice, right? And so you can see that these less expert doctors, the IM/EM doctors, are a little bit less diagnostically accurate, but it's not significantly different between the two advice types. In fact, they're a little bit more accurate with the AI advice, and same for the expert radiologists. So even though radiologists trust the AI advice significantly less, they perform a little bit better with it, okay? The really interesting thing is even, so forget about where the advice comes from, because you can see here, there's no significant effect of the source of the advice. The kind of advice does matter. So experts generally have better diagnostic accuracy, right? So if we just draw a yellow bar up here, right, to say the same level of diagnostic accuracy across both the experts and the non-experts, you can see that far more individual radiologists here, from about participant 70 to participant 138, are above this line, right? So a lot of radiologists have a high accuracy, a high diagnostic accuracy, whether we gave them accurate or inaccurate advice, okay? However, the IM/EM participants have a lower diagnostic accuracy, right? And so this might be expected, right? Experts should have a higher diagnostic accuracy. However, when you look at what happens in these settings where the bar is only blue, that means that this doctor, so Dr. 60 here, who's a radiologist number 60, and also IM/EM doctor number 60, they only got cases right when they were given accurate advice. So every time a red patient, right, this doctor over here, Dr. 40, got several blue patients right, and then one red patient right. Same thing with Dr. 40 down here. But these doctors, highlighted by these red boxes, only got patients' diagnosis right when they were given correct advice. So some doctors are more susceptible to incorrect advice than others, regardless of the advice source. And so this led us to think we really have to be careful about the advice that we give. It's not just about AI, right? Doctors will listen to incorrect advice because of this strong anchoring effect. There's another paper that has shown something very similar. It came out this year, Human-Computer Collaboration for Skin Cancer Recognition. And the paper is not actually about this, but hidden in figure 2 sub figure I is this one graph that I think is very important, where the entire rest of the paper is about how much better people do, clinicians do, at various levels of expertise when you give them a model to work with, right? And the point is, you can make much better clinical decisions when you have AI support that's collaborative. However, they have this one very small subfigure that shows, yes, you can get these lovely beneficial gains, especially for less experienced clinicians when you give them good advice. But if you give them the wrong AI, right? So if you intentionally make the model incorrect, the damage that you see, the loss in predictive accuracy that you see across levels of experience far surpasses the effect that we saw that was beneficial when the model was correct. And so this for me was a huge takeaway from that paper, even though it's a very small portion of it. Because to me, this is sort of warning that advice can be dangerous. And explainability, I would like to state very strongly, is not a panacea to this. So recent work on the interplay between machine learning and human decisions, for example, in predicting the ultimate rental price in the New York housing market, has shown that clear models don't actually improve your ability to have a final prediction that is accurate. In fact, models with more transparency that people believe that they can understand more hamper human ability to detect when a model makes a serious mistake. And models that are more transparent, the authors note in this study, probably make people feel like their choice is good. It agrees with the model. I understand this model, therefore I don't need to do a more aggressive audit. And you might say, well, that was just in the New York housing market. That's very different than what happens in medicine, right? You know, medicine is about evidence and science, and decisions about routine clinical practice should be justified by evidence or in evidence, right? However, healthcare decisions often, especially in routine practice, are contradicted in the future. So this is not a small proportion. So in the last 10 years, it's over 10% of these, so that's about 400 papers have come out in top clinical journals, things like JAMA, Lancet, the New England Journal, that have said this routine practice that we do is actually harmful. We should not do it. This is a medical reversal. Other things to be concerned about are we don't audit doctors regularly for accuracy or performance. So for example, in the United States, there are medical boards per state that can review complaints that have been made about clinicians, but is up to the purview of these boards, which are often comprised primarily by clinicians with some non-clinical members, to decide what wrong has been done and whether action should be taken. And finally, it's been established that individual doctors have strong preferences, both about which patients they like to treat and about what treatments they like to give for specific conditions. And so there is a lot of individual variability in what practices clinicians do, what patients they like to see, and even in what evidence they think they're supposed to be following at any moment. There are some good arguments for explainable models that I'll go through and then identify my disagreements with. The first is, if it's a principle or a regulatory standard like GDPR, where you state that people just have this right to logic about algorithmic decisions, I think that's a fair argument. And in that case, regulatory bodies should make a decision about how that logic should best be given to different kinds of expert and non-expert end users. However, if your argument is that explainable models are needed in high-risk situations because experts just need them, right, in order to justify decisions, let's think about that for a little bit, specifically in the use case for clinicians. It's probably important to have an explanation or transparency of some kind when clinical opinion differs significantly from the predictions you're giving. This doesn't mean that clinicians actually care about how the model works. Most clinicians don't know exactly how an MRI machine works. It also doesn't mean that you build simple models for the sake of transparency, because as we saw in the New York housing market, that doesn't actually help. It could mean that you want to understand when to rely on or reject model outputs, or that you need a notification of what populations the model might work or fail on, or that you just want limitations of the data that the model was trained on. Some technical options for this are: one, transparency via post-hoc explanations. This is a very popular way of doing transparency for your models. They're only really useful if they're consistent. What I mean by consistent is different model behavior has a different explanation, and the same model behavior has the same explanation. So attention-based explanations and saliency maps are not, by definition, consistent. There are possible fixes to make them consistent that have been identified in the past couple of years, but these are not the canonical vanilla forms of attention or saliency maps. There are other forms of post-hoc transparency that people have identified, like LIME or SHOP. And again, these have been shown recently to not significantly help robust classification, either on their own or under attacks. Here's an example of something that my group has used post-hoc explanations for. So I told you what I wouldn't use them for. Here's what I would use them for. Let's say you want to predict interventions in the intensive care unit, and you've been given a lot of data. So on about 34,000 patients, you've been given a bunch of static data like gender or age, a bunch of time-varying data like oxygen saturation, respiration rate, lactate levels, and then all of the clinical notes for each patient's stay. You process each of these independently, concatenate them into one large matrix. So every hour you have a large set of features per patient. And now you have a big tensor across all patients because each patient is a big matrix. And there are many ways that you can model large tensors of hourly data like this. I'm going to focus on the two deep neural network approaches that we use because these models are often attacked as being black box. So recurrent and convolutional networks. So what we did is we said the clinicians wanted to know, can we give you less information next time so that you can make the same quality of prediction, but using less data? And so we did feature level occlusions where we removed some data and saw how AUC performance was impacted. And so you can see here that physiological data was more important for predicting invasive tasks like needing a ventilator. However, the topics that we learned from the clinical notes actually were more important for less invasive interventions like a fluid bolus. Another thing we did is clinicians wanted to know, well, what do these patterns actually look like when they're being activated for something like needing ventilation? And so we went through and looked at the convolutional filters that had the top and bottom trajectories for ventilation, for example. And then the clinician said, well, that looks like hyperventilation because I see in these top 10 trajectories versus the bottom 10 trajectories that there's higher diastolic blood pressure, higher respiratory rate and heart rate, and a lower oxygen saturation. Okay, so that's one example. So again, we weren't using it to try to have the clinicians trust us at deployment time or feel comfortable with the model performance. This was about auditing what kind of information is necessary and trying to understand with the clinicians as we're developing the model, what kind of trajectories are being learned and whether we can map that back onto their priors. Another thing that we've done is modeling specific latent variables effect or specific side channel information effect on the reconstruction of a particular model. So here, for example, we're trying to see what the morphological change to a cell line will be under different concentrations of a particular drug. And so as we move the concentration of the drug, we wanted the model to have one axis for side information in its latent variable space where we could independently modulate it so that the clinicians could look at, here's what we think a cell might look like under a higher or lower concentration of this drug. Okay. Option 2 is transparency through natural outputs. And so this argument is that, well, if transparency is just a way of calibrating a clinician's trust in a model, then maybe we can have clinicians and machine learning experts agree on a set of metrics that are a consumable end product, not an intermediate risk score that we then need to explain. And then we can deliver those metrics, those things we agreed on as an end product, and that gives us transparency by definition. So the example here is, what if we created reports from clinical images? So automatically generated radiology reports from the chest X-ray images that were provided. So importantly, this is not like image subcaptioning where models like show and tell or show attend and tell work really well, because in subcaptioning, you need to comment on what's there, like the girl in the pink dress is jumping in the air. And in chest X-ray reports, you have to predict what somebody might have thought could have been in the chest X-ray and then comment on the presence or absence of that in the X-ray. So it would be like saying, the girl in the pink dress is jumping in the air. There are no helicopters and she's not bleeding. So you have to first predict the topics that might be meaningful for the report. And then you need to conditionally generate sentences corresponding to those topics. So we achieved this with the CNN, RNN, RNN architecture. This lets us have these largely templated sentences still generate diverse text. So X-ray images are encoded. Then this embedded image representation is fed to the first RNN for sentence level decoding, and that's sent to a second RNN for word level decoding. And the thing that we did differently here, as opposed to the last sort of model that tried to identify how best to do reports from images, is we added a clinical coherence reward in addition to a natural language generation reward. So what that means is we wanted to make sure that the generated report was not just human readable based on some of these automatic readability metrics. We also wanted to make sure that it had the same diagnoses, the same disease states as the ground truth report. And by adding in the clinical coherence reward, we're able to have much higher clinical accuracy as compared to other models. So you can see down here, they're lower. But we aren't sacrificing this natural language readability metric, right? And so here you can see that the natural language metrics, ours is pretty close to competitors like TiNet. But really where we're improving is with disease accuracy, because we've delivered on this end product of having a report that is both clinically accurate and is human readable. A final option, if you don't want to do any post-hoc transparency audits, or if you don't want to have your model deliver something that is the consumable end product, is you can just audit the data itself and try to understand how people are using it and what sort of confidence they should have in model outcomes. And the reason that this is important is because algorithms require large-scale data sets for research use often. And so we want to make sure that this really valuable health data, this embodied data from human bodies, is being used correctly. So there are some really cool tools for doing this, things like data sheets for data sets or model cards for model reporting. These are really nice because they're so-called big picture tools that are trying to help you work towards transparent processes, not just a transparent model. The last thing that I want to cover is the argument that transparency is important for fairness, and that black box models could create, increase, or propagate biases. So I agree with this. However, I would like to say, first of all, bias is already a really strong part of the clinical landscape. So doctors are humans and humans are biased. So guess what? Doctors are biased. And so that means that there are lots of lovely publications. These are not machine learning based. They're all clinical or epidemiological that have established that the societal biases you might expect are also present in clinical care. And one way that this might show up in your machine learning model is in a fairness audit. And so there's some nice work that's been done in recommendations for how you should audit the performance of your models across different ethnicities, different kinds of insurance, if there's variation in insurance type, and different genders, to ensure that you don't have worse prediction accuracy in one group versus another group. And then there are ways of rebalancing that fairness. Fairness audits are very hard to do robustly, though, because sometimes it's hard to imagine just how deep the bias goes. So we took a model, Cybert, which is one of these contextual language models that's trained on scientific articles, on PubMed. This is not the internet, with all of its racism and trash. This is just PubMed, okay? So we took a model, language model that's been trained on scientific articles, and we gave it a prompt with where we're going to fill in one token, and it's going to fill in the blank on these two other tokens. And this is a real token taken from a real clinical note where we just took away the race and the outcome. So the sentence is, race, patient became belligerent and violent, was sent to. If you're Caucasian or white, the model thinks you should be sent to a hospital. If you're African, African American, or Black, the model thinks that you should be sent to prison. And again, this is not a model that was trained on random text. This is text from scientific articles. And so again, this is a very pernicious bias that you would have to work very hard to even identify as being present in the model, right? It's unclear that we can find all the biases and audit for all of them. So how do we improve care and practice? Well, this is inspired by a comment that somebody gave when I gave a presentation on my work a couple of years ago, where they said, I understand what your work is trying to do. You're trying to make algorithms that are, fantastic doctors like Dr. House. And my comment then and now is, actually, no, he was a bad doctor. Have you seen that show? He was a drug addict. He was mean to people. This is not the kind of doctor that most people want. And I think that what we need to be aware of is that many doctors are burnt out. And this was taken in non-COVID times. I'm sure this number is higher now. And burnt out doctors feel like they don't have the time to be empathetic. And so something that I think would be really helpful in practice, and the way that I think we should pivot in the future with work in explainability, transparency, and justification, are trying to support clinicians as they do tasks, but that's probably going to be very task specific, and I'll tell you why. We did a project a couple of years ago where we thought we were going to train machine learning models that could give you a score and that would improve your accuracy on a task, okay? But first we needed a baseline. And so we took a medical record system that's very ugly, based on tables, you know, looks like a standard medical record system. And then we were going to compare clinicians' accuracy and confidence using that system to what happens when they had a much prettier system, you know, a nicer user interface for the same data. No model-based recommendations, no AI advice. We just wanted to say, here's our baseline for ugly interface versus pretty interface. And then we were going to add machine learning. And the task that we gave, and these were real healthcare professionals looking at real medical records, is we asked them to plan for 2 potential interventions in an electronic or intensive care unit ICU simulation. So we said, here's patient data. Do you think this patient will need a vasopressor? Do you think they'll need a ventilator? And how confident are you of that? And what we found is that giving people the information in a much nicer form raised their confidence a lot, but it did not make them significantly more accurate. And that's really important because we don't want to have people feel very confident in their performance if they're not accurate. So how do we improve care and practice without making people worse at their jobs or potentially just as bad at their jobs, but just much more confident that they've done the right thing? I think then rather than making a new risk score or explaining it or having some transparent model, we should try to improve processes that exist but are faulty. And so the example that I have for this, and one of the things my lab is working on right now, is think about a process that doesn't work well and how it might be fixed. So there's a really nice study that was done a couple years ago that showed that gender concordance increases a patient's probability of heart attack survival. And the effect is driven by increased mortality when male physicians treat female patients. That's really depressing. It means that female doctors are able to recognize what's happening in male patients equally well as for female patients, but male doctors disproportionately let female patients of heart attack die. There's a very interesting direct quote in that study that is strange, but again, very thought-provoking, which is, mortality rates decrease when male physicians either practice with more female colleagues or have treated more female patients in the past. The female patients one makes sense, right? If I see more examples of women dying of heart attack and afterwards learn she died, she was having a heart attack, you should have treated her this way, I'll be better at it next time. But having more female colleagues, that's a really interesting one. Is that because you see them listening to the right things? Is that because when they see you making a mistake, they tell you, hey, this is actually a heart attack, you just haven't noticed it? So this led us to think maybe what we really need is human and machine learning in the loop, meaning these are opportunities to collaborate where we could try to use machine learning models, not to make a new fancy risk score that's better than a doctor or to explain a black box model so that the doctors feel comfortable in a poor decision that they've made, but to try to train doctors so that as they are learning, when we detect something that might be a mistake, we give helpful prompts, a lot like those female colleagues are likely giving to the male physicians who are not recognizing female heart attack symptoms. So in summary, I think that explanations and transparency are very important in debugging and audits, as shown in the work that I've done that uses them today. I think it's unclear how any expert or non-expert user ever could or should incorporate them. I think experts have, other experts in robotics have shown that explanations cause over-reliance. And several studies have shown that they also reduce your audit propensity, which is really, really frightening in cases like healthcare. And biases that could be created or increased or propagated should be tackled with these aggressive audit standards that regulatory bodies should set, because it's hard for us to come up with them on the fly for different areas of research. And then researchers and implementation teams should be held to those standards. This is all work that's been done with a fantastic team at University of Toronto, Vector Institute, several of my clinical collaborators at neighboring hospitals. And I think that there really is a huge opportunity to create actionable insights in human health. Thank you.